All right, we will be doing a lesson on piecewise functions. It is not actually a section in your textbook, so there's not going to be any bookwork. But it is a very important concept for Algebra 2. Before we talk about how to graph a piecewise function, though, let's talk about something we do know. This guy right here, f of x equals 2x minus 1. If I asked you to graph this, we would have to recognize that is in the form y equals mx plus b, so it's a line that I'm about to graph. And I start by graphing y-intercept down here at -1. And then the slope is a 2 over 1, which means rise up 2, run right 1. So I'm just graphing a line, old line problem. Now instead of going up 2, right 1, I could also go down 2, left 1. Very good. And then on a good day, I'd be able to connect these. Ooh, not a good day. Not a good day. All right, there we go. Pretend that was a straight line. It's not. Now, that was a very boring Algebra 1 problem. What if I said, same function, but I am going to restrict your domain? So same function, but this guy only exists when your x's are greater than or equal to 3. So I'm going to go back to my picture, and I'm going to restrict the domain so that my x's are greater, whoops, not equal to, didn't it just say greater than 3. So I'm going to take a highlighter. I'm going to mark where x equals 3 is, which is right here. Okay. Whoops. Again, pretend I could draw a straight line. I can't. Not boding well for us today, guys. And here's the issue. Because I've restricted your domain, I have to erase half of this line. Yeah, because it says right here, only x's that are greater than 3. So which part should I erase? This part. So I have a follow-up question for you. What about the point at x equals 3 that was on this little green line? Is there actually a point there? No. Because it's not equal to. Very good. What used to be a line, what does it look like now? Array. Very good. Simply because I restricted the domain. And I can do that because I'm your teacher. Now, this is the essence of a piecewise function. Depending on what part of the domain I'm looking at, I'm actually going to be looking at a different function. So everyone should have 2 colors and 1 highlighter handy. Got it? So in our old textbook, this used to be called section 2.7. It's not called anything in our new textbook. So, and good news, we're re-recording the lesson. So everyone from here on out will just know to Google piecewise practice. All right, we have 2 tasks today. Our first task is to understand what a piecewise function algebraically looks like. We're going to evaluate that algebraic function. We're going to graph that algebraic function. So this first example, his name is f of x, and this is the function itself. Off the top of your head, can you tell how many pieces are in this piecewise function? At first glance, a lot of kids say 4. There's actually only 2. This is the first piece to the piecewise function. Take your first color and box that in somehow. You can use a highlighter, but in the future, we're going to use this green, like I'm going to use green to graph. So if what you're using is not good for graphing, maybe use something else. And then this bottom guy here, which I'm going to box in blue, that's the other piece to my piecewise function. If those are the 2 pieces, then what the heck is the stuff off to the right? Those are the domain restrictions. It says use this top function, and then it says if your x is less than or equal to 4. It says use this bottom function if your x is greater than 4. So it's instruction. It tells you when to use which function. So our first task is, how do we evaluate this? So let's look at if x equals 10. I know you probably didn't use the same colors as me, so I'm going to refer to this as the top function and the bottom function. So if x is 10, should I be looking at the top function or the bottom function? Why the bottom? That's right here. Use the blue function or the bottom function if your x is greater than 4. 10 is greater than 4. So I'm going to take my blue pen. I'm going to say 2 evaluated at 10. So 2 times 10 plus 7, better known as 27. So new problem, but the same function. Now, What if I want to evaluate that piecewise function at negative 1/3? Would I use the top function or the bottom function? For negative 1/3. I heard top. Tell me why. Yeah, negative 1/3 is less than 4. So using my top function, but this time I'm going to plug in a negative 1/3. You see the reason for the colors now? Teacher is good, teacher is wise. 24 hours from now, you're going to be really confused if you don't have colors, guys. If you change your mind and you want colors now, go get some. Negative 1 minus 1 is negative 2. Yes, sir. What about x equals exactly 4? Yes, the top one, because that's where the equal to 4 symbol comes in. So 3 times 4 minus 1, that would be an 11. But once in a while, I hope you aren't this kid, I get a very weird child who wants to be really thorough. And they're like, you know what, Abruzzo? I am going to plug in 4 into both functions. And then I'm going to write them both down. Because one of them's right. They just scored a 1. Yeah, a kid who does that has like zero understanding of what a piecewise function means. Don't be that kid. Like, that's way bad. So, understand that a piecewise function, each piece only works for certain parts of the domain. We got to watch out for that. Okay, negative 2. Same function, same restrictions. Negative 2. Should I use the top function or the bottom function for negative 2? Top, because negative 2 is less than 4. Good. So 3 times negative 2 minus 1. Negative 7. And how about 5.2? Function or bottom function? 5.2 is surely bigger than 4. So we should be using the bottom function. So 2 times 5.2 plus 7. 10.4 plus 7 is 17.4. We're good with why I use the bottom function? All right. So that's your very quick intro to what a piecewise function looks like and how we evaluate it. Let's try another couple examples. So in this section, up at the top, there's f of x. Everyone say hi, f of x. There, good. Here's g of x. Everyone say hi, g of x. Yeah, good. Thank you for cooperating. And then say hi, h of x. Salutations. The reason I just made you cheesily say hello to functions is because we got to understand that f of x, g of x, and h of x are the names of each of those three functions. So you should notice that this first row of problems wants you looking at which function? F. So make sure you're only looking at function f. Now to make things extra exciting, function f is very weird. The top function is 3. And the bottom function is 2. And the restriction on the domain splits at 0. So it says use this green function if your x is less than or equal to 0. Use this red function if your x is greater than 0. Now the domain restriction wasn't weird, but the actual functions are weird. You notice something seems to be missing in these functions. There's no x. Like usually I have you plug into the x and do your work, but these are called constant functions. Constant functions are kind of boring, sorry, because there's no math involved with evaluating them. They constantly give you the same output. So like, for instance, if I'm going to the green function, what output is it always going to give me every single time? 3. So no matter what you try to plug into the green function, it's going to keep pushing out a 3, a 3, a 3, a 3. And then same thing with the blue, except on the blue function, what output is it constantly going to give you? A 2, a 2, a 2, a 2. So in this particular set of examples, very boring math is about to happen. Hang with me. What if I take function f and I want to evaluate it at 2, which means I'm trying to plug in an x equals 2. Top function or bottom function for x equals 2? Bottom function, because it says right here, use me if your x is greater than 0. Normally at this stage, I would say please plug in a 2 into the bottom function. But what's always going to be your output on the bottom function here? 2. That was boring. Okay, how about -4? What if I wanted you to plug in a -4 for your x? Now we're on the same function over here. So top function or bottom function for -4? I heard top, cute, because -4 is smaller than 0. So normally I would say plug into the top function, but very boring function. What's the output? 3. How about exactly at 0? Top function or bottom function? Top function again. So again, normally I would have you plug in, but boring, 3. And then 1/2. Bottom function, 1/2 is greater than 0. So normally I would say plug in the 1/2. A little boring because it always comes out to a 2. That was a very special circumstance of you having a constant function. Me personally, I would be very happy if I saw a constant function because it's easier. They're just weird. All right, this next row, what do you notice every single thing wants you to do in this next row? G, 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 G. We're looking at function G. This time we have more exciting functions. I'm going to try to stick with the same coloring. Top function for me is green, bottom function for me is blue. And this time the domain split happens at 3. So if you're less than or equal to 3, use the top function. If you're greater than 3 for the x, use the bottom function. So let us talk about the first question, g of 7. Top function or bottom function? Bottom function, because 7 is greater than 3. So this time I will have to do a little bit of math. 2 times 7 minus 1, which is 13. Okay, how about 0? Do I use top function or bottom function if I'm plugging in a 0? Oh, 0 is bigger than 3? Top. Like we said, top. Top function if your x is less than 3, which 0 is less than 3. So I go ahead to the top function, I plug in a 0, and I get 5. How about -1? -1 is less than 3 again, so top function again. -1 plus 5 comes out to a 4. How about exactly 3? Top function again, so plugging in a 3 on the top function gives me an 8. Take a little bit of getting used to, for sure. You have to understand the translation of the algebra. So up here in the green says x plus 5 if your x's are less than or equal to 3. But it's 2x minus 1 if your x's are greater than 3. All right, I'm going to skip the next row just for the sake of time. There's nothing wrong with function h. He's a great function. I just don't have time. Oh, and it's got fractions. Automatically we skip it. Is that what you're saying? Okay. All right, let's talk about graphing. This is the good stuff here, guys. Okay. I promise you that after we finish the first example, you're going to think like this is the worst thing ever. And then we're going to do another example, and then you're going to go, okay, it's not that bad. And then after the third example, give me 3 full examples before you start whining. It'll be okay, I promise. After 3 examples, you'll feel good. But okay, you might not love it, but you'll be able to tolerate these problems. Yeah. But you got to give me 3 examples before the whining starts. Deal? 3. Internet, they're not believing me. I just want you to know that. They all look skeptical. Okay, first thing we're going to do is identify with colors, whatever colors you're using, and some of you are now believing me that yes, colors are the way to go. Top function, I always use green. Do whatever you need to do. Bottom function, blue for me. Now, since I'm going to be graphing, I work best with boundaries. So I'm going to take my highlighter now. Grab your highlighter. And we're going to mark the boundary line. The boundary line is where your domain split. Can you tell where your domain is going to split? 1 at x equals 1. So at x equals 1, you need to kind of graph some sort of a line down here. And it's not part of the function. It's just there to help me visualize that something weird happens at x equals 1. We're not going to erase. I'm going to teach you a different way. A good question was brought up. You've been delivered some information by a outsider, huh? Some of the other Algebra 2 teachers teach this a different way. I have literally 4 different ways I could teach you this lesson, and they're all very different. I just go with this method because I feel like this is the easiest for most kids. But if this isn't sitting with you right, and you're like, you know what, I hate this way, I'll teach you another one. Okay, we'll start with this one. Okay, whenever I am introduced to a new function that I'm not really familiar with, I like to start with a t-table, some sort of an input-output table. So the problem here is you've got 2 parts of your function, which means I have to treat them differently. I have to basically do 2 different t-tables. So using my first color somewhere off to the side, like right here maybe, I'm going to make a teeny tiny t-table in green. And the way t-tables work, you get to choose the input. So like I can technically pick any x's I want. They need to make sense for my problem. And then because we're piecewise, they have to follow whatever rule I am given. So the way we start on a piecewise function is I always start on the boundary line. That's a good starting point. So what was the x value on the boundary line again? 1. So put a little 1 there. And then for my next x value, it is your choice. But remember the rule says this function is only for x's that are less than or equal to 1. So give me your favorite number less than or equal to 1. But not 1 because we already did 1. I heard 0 would work great. I heard -5, that's fine. -12. Okay, get a little too creative on me because if I start doing like -12, do you see what the problem's going to be? Yeah, I'm going to fall off the graph. It doesn't mean it doesn't exist. It's just for like someone who can't draw, I need all the help I can get. So I'm going to go with 0. That sounded logical. Definitely smaller than 1. I don't need any more points. Are you already evaluating it for me? Okay. So you're all about business today. We need the y counterparts to these ordered pairs. So this is where you do have to do a little math. I take the x that you chose and I plug her in. So 2 times 1 minus 1 is 1. And then I do the same thing with a 0. So 2 times 0 minus 1 is -1. What y'all just came up with are 2 ordered pairs that I'm going to be plotting shortly. Don't do it yet. The reason I didn't want you to plot them yet is because the boundary line point, the very first one we came up with, I have to ask myself if that point even exists or not. And the reason I know whether it exists or not is I look at the inequality. Does this first green guy exist on the boundary line? He does. Why? As an equal to bar. So when I go to plot the boundary line point for this green function, I'm going to use a filled in circle on the boundary line. We'll talk about why this is important in just a few minutes. But 1, 1, filled in circle, boom, on the boundary line. And then my other ordered pair you guys came up with was 0, -1. Boom, right there. If I'm not on the boundary line, I don't have to think about like open and close. It's just a point. Okay. Now you get to connect the dots. It stems from the boundary line outwards. So from the boundary line out, pretend that was straight. Definitely not straight. Oh, that's worse. Okay. Okay. Yep. Yours looks real good, right? Use your imagination on mine. Are we done? No, why not? I have a whole other function to talk about. Okay, other function. Little t-table, blue guy. I have to do the boundary line. Always, that's my first point. So that would be a 1. Now, your choice as to what my next x value is. Just make sure it follows the rule where it has to be greater than 1. That sounds logical. So go find his y counterpart by plugging it in. So 3 times 1 plus 1 is 4. And then 3 times 2 plus 1 is 7. So each one of these ordered pairs I need to plot, but not yet. Hold on. Remember how I made you stop and think about that first boundary line point? This first guy? I want to know if that point even exists. Or if maybe I have to put an open circle. And for that, you look back right here. Open circle. Why does it have to be an open circle? Does not have an equal to bar on the boundary line. Okay, so using my blue ink, I'm going to put an open circle at 1, 4. And then I'm no longer on the boundary line, so you're just plotting regular old points, 2, 7. Then play connect the dots with me. Again, pretend that was straight. Now, that is what your piecewise function looks like. When I finish graphing a piecewise function, there's technically three things I look for, okay? For Algebra 2, we keep it pretty basic. You're going to have two rays going in opposite directions of the boundary line. So one goes to the left side of the boundary, one goes to the right side of the boundary. If you have two rays on the same side of the boundary line, like both going left, you screwed up. So that's my first way of checking if you did it right. Next thing I want to check for is that only one of the rays has an open circle and one of the rays has a closed circle on the boundary line. So if they both have closed circles, you messed up. If they both have open circles, you messed up. That can't happen for us in Algebra 2. Okay? Okay, I told you. 3 examples before you start whining. Give me 2 more. 14. Here's my top function in green. And then here's the bottom function. I'm going to do this one in blue. And then this is a sheer coincidence, guys. The boundary line is still located at x equals 1. They're not always going to be at x equals 1. So grab your highlighter. Mark up x equals 1 again with your highlighter. My goodness. Awful. Yep, very good. Okay, good connection, she said. Yes, yes. Because, oh well, for us, yeah. You guys are asking great questions. They asked about, is the boundary line just domain restriction? Yes. It's the point in which your domain switches the function. And the next question was, will they always be the same number? For us, yes. There will be times in your future possibly where you see multiple pieces in a piecewise function, like more than 2. You can have 47 pieces of a piecewise function. And in real life, they do. We aren't going to graph those, though. So we will see piecewise functions in our future where there's 3 pieces. You're going to see 2 boundary lines. It happens. It's okay. All right, let's get graphing. So I'm going to take this green function, and I'm going to create a little t-table off to the side, a very little t-table. And who remembers where I always start off my t-table? At the boundary line, so for us it's a 1. Now you get to choose another x value, just make sure it makes sense for my problem. This green guy is only for x's that are less than 1. 0 sounds wonderful. Did anyone go with something other than 0? -2, just to be fun. Woo. All right, let's figure out their y counterparts. Look at a 1. So 1/2 times 1 is 1/2, or 0.5 if you prefer decimals. And then plug in a 0. 1/2 times 0 is 0. So what you have here are 2 different ordered pairs, but before we plot them, I want to talk about this first ordered pair, the boundary line ordered pair. For this green function, open circle or closed circle? Open. Why? Yes, because, oh, tablet, don't ruin. Because right here, it says for the green function, it's only when x is less than 1. But when we're right at 1, I can't draw a point. It'll be an open circle. All right, so the point 1, 0.5, very difficult to draw in here. I apologize. Just really exaggerate the open circle, guys. I'm really old, so my eyes don't work as great as they used to work. So when you draw your open circles, make them real exaggerated. The other thing that kids usually do, because we're using markers, is they they'll fill in the point and they're like, oh, drats, that was supposed to be open. So if that happens to you, just draw like an arrow and then write open, and I'll know what that means. It happens. All right, the other ordered pair I'm supposed to plot is 0, 0. Anything off of the boundary line is just a point. You don't have to worry about open circle, closed circle. In fact, Because I already drew an open circle, do I ever have to worry about another open circle in this whole problem? Nope. All right, connect the dots from the boundary line outwards. There you go. Half done. Only half done because you got a whole other half of the function. Let's do this. So a little mini t-table for my blue guy. First ordered pair has to come from the boundary line. So that was 1. And then choose any x that's this time greater than 1. Wow, getting crazy on me with a 2. All right, if I plug in a 1 to this function, that's negative 1 plus 3, which is a 2. Then if I plug a 2 into this function, that's negative 2 plus 3, which is a 1. That was oddly symmetrical. Did you do that on purpose? Maybe. Totally intended that. And I know some of you are working ahead of me, and that's awesome. If you're picking different points, it does not matter because you're going to end up on the same ray further down the ray. We already discussed this, but is it going to be an open or a closed circle here for this first ordered pair on the boundary line closed? Yeah. And the reason is because it's got to equal 2 bar. The other reason is because I already used an open circle. So at 1, 2, I got a, oops, wrong color, closed circle. And then at 2, 1, I got another point, I should say. And then from the boundary line outwards, connect the dots. Oh, look at that. So a couple things I double check here at the end. Are my rays going on opposite sides of the boundary line? One outwards. Yeah. On the boundary line, is there just one open circle and one closed circle? Yeah. I'm feeling good. Number 15. Okay. Top function, I'm always going to do in green, keep it consistent. Bottom function in blue. This time, for a little variety in your life, your boundary line is no longer located at 1. Where's our boundary line located this time? 3. I'm going to highlight that boundary line. And it's time to get some points. What point do I always start with for my piece of the piecewise function? Boundary line. And who's your boundary line this time? 3. Now for this green function, you got to choose things that are bigger than 3 when you're choosing. 4, get crazy. All right. So if I plug in a 3 to this function, 3 plus 2 is 5. And then switch it up. Plug in a 4 this time. 4 plus 2 is 6. So you just found 2 wonderful ordered pairs. Why am I only choosing 2? Like, why not 3 or 4 or 5? Yeah, in order to graph array, you only need 2 points. So, could I ask you to graph 3, 4, 5 points? Yeah, we've got enough to do. 2 points is good. All right, before we plot, can we talk about this first ordered pair? Is it an open circle or a closed circle for this first green function here? Open. Why open? Not equal to 3. Very good. So, green guy, open circle at 3, 5. Boom. And then a normal point at 4, 6. And then you need to play connect the dots from the boundary line outwards. I had children call this lesson fun today. Fun. You think it's fun? Is it the colors? Is it the colors that do it? I don't know. Fun is not really the adjective I would use to describe this myself, but whatever. Unique and interesting, yeah. All right, the blue function. New t-table because we got a new function. Where do I have to start the piece? At 3, good. And then choose anything less than 3 after that. Declare for going there. Yeah. All right. Are you going to get crazy and choose like a negative 4? No? All right. All right, plugging in a 3 to this function. 3 minus 3 is 0. And then plugging in a 2. 2 minus 3 is negative 1. Great. This first ordered pair, the one that's on the boundary line, I think I already know the answer to this. Since the first one was open, this guy probably is closed. Tell me why it's closed. Got an equal to bar on the 3. Very good. All right, so close circle at 3, 0. Boom, right there. And then a regular old point at 2, -1. Boom, right there. Connection from the boundary line outwards. Oh gosh, that was bad. Oh, that's worse. Okay. That was supposed to be a straight ray. So, double check. Do I have one open circle and one closed circle on my boundary line? Yes. Are my rays going on opposite sides of the boundary line? Yes. All right. Let's skip 16. Obviously, because of this fraction. No, we're timed. Let's do one more. This fun one has a boundary line at 0, so I'm sure glad I have a highlighter when I go to highlight this. It's so hard to highlight 0 otherwise. Top function is x plus 3, bottom function is 2x. Boundary line at 0. Oh, they're real fun. There's like smiley faces and yeah, rainbows, daisies. We'll get those out later. We gotta make this fancy for you. No, we can't be using. All right, obviously. So this cap function, when I go to make my t-table, I have to start on the boundary line, which is where? 0. And then I got to choose another thing that follows the rules here. It says less than 0. Oh, getting crazy. -1. Okay. Plug in a 0 to this green function. And then plug in a -1 to this green function. You guys are good. All right. Before we get plotting, we need to talk about that first ordered pair. This guy that's on the boundary line, 0, 3, open or closed? Closed. Very good, because it's equal to 0. But 0, 3, I got a green closed circle. Make them real exaggerated if it's hard to see, especially for your old-eyed teacher. And then -1, 2. And the connection goes from boundary line out. Okay, pretend that was straight. Sure wasn't. All right, my next function. I have to start on the boundary line of 0, and then I got to choose values for x that are greater than 0. 2, oh man, shaking it up. All right, if I plug in a 0, 0 times 2 is 0. If I plug in a 2, 2 times 2 is 4. So here's my first ordered pair, here's my second ordered pair. What kind of a point are we talking about for this first one? Open circle or closed circle? Open, because it is not equal to on the boundary line. So 0, 0, we got a enlarged open circle because I don't want to like have to squint to figure out if it's open or not. And then 2, 4. And then connect the dots from boundary line outwards. So we're going to stop the lesson there. Thank y'all.